Hello, everyone. Today we're going to be looking at graphing. I know it says an introduction to limits, but this video is specifically for students that need to review their graphs. So if you think that you can make all the graphs in this section without this video, by all means, you can skip to the next one. But this is just a great way to review from pre-calculus and make sure that you remember all the different graphs that we've learned. So we're going to start with the first one. I'm, like I said, going to ignore the limit, and I'm just going to be looking at y is equal to 2x plus 1. We're going to be graphing a line. The standard form for the equation of a line is y is equal to mx plus b, all the way back from middle school. So you've got a slope of 2, and you have a y-intercept of 1. And honestly, if you have those two things, you can graph it super quick. Y-intercept of 1. Remember that in this class, whenever you state a y-intercept, if you just state it as 1, you will lose points. It's always the ordered pair 0 is equal to 1. Saying y is equal to 1 is a line, not a point. So make sure you do that. And then from there, slope is rise over run. So it doesn't look like it has a denominator, but it's 2 over 1. So I'm going to rise 2, run 1, rise 2, run 1. And then you can go back 2, down 1, back, and finish out your line like that. Quick review of lines. Next, we're going to do a parabola. So we're working with y is equal to x squared minus 2x plus 1. There's several different ways to graph a parabola. I'm just going to tell you right now that 90% of the time, I'm going to graph it by factoring. I think it's the easiest way to graph a parabola when you just want the general shape. Factoring always produces the x-intercepts. Now, in this case, there's only one x-intercept, which you may remember that when a factor is repeated, it means it bounces. So I know that the x-intercept is 1, and I know that it's going to bounce at 1. It's an upward parabola because a is a positive number, which is positive 1. And because it doesn't have an a greater than 1, or I should say different than 1, you can use your basic points. Pretend that this is 0, 0, and then go 1, 1, 2, 4. In the other direction, 1, 1, 2, 4. And I've graphed a nice parabola. An alternative method for graphing the parabola would be to use negative b over 2a. This always produces the x-coordinate of the vertex. So in this case, remember that a is here, b is here, c is here. So negative b, or the opposite of b, would be 2 over 2 times, and in this case, a is positive 1. 2 divided by 2 is 1. So that's the x-coordinate of the vertex. It's still your job to go back in and plug 1 in. And if you plug in 1, you'll get 0, which we already knew. So either way, you can find the vertex using negative b over 2a, or you can factor and find the x-intercepts. But either way, that's a little reminder on how to graph a parabola. Next, we're going to graph a rational function. The two most important parts of the rational function are the vertical asymptotes and the horizontal asymptotes. So we'll do vertical asymptote first because it's just so nice and easy. The vertical asymptote can always be found by letting the denominator equal 0. So in this case, x plus 2 is equal to 0. Solve that, and you get x is equal to negative 2. You have literally just found the vertical asymptote. The horizontal asymptote can be found by looking at the coefficients A over B when the powers of the variable, usually x, are the same. So since they're both x to the first power, I can look at their coefficients. It's 1 over 1. So y is equal to 1 is going to be my horizontal asymptote. There's other parts of the horizontal asymptote, but there's other examples that I'll do it in. So y is equal to 1. Now, if we were in pre-calculus, I would definitely want you to plot at least 2 points on each branch to make sure you had a really nice graph. We're actually going to be studying limits. We mostly just want to know the general shape. So we are going to just pick a point and plot it when you can. Pick 0. It's so easy. So if I pick 0 for x, I get 3 halves, which is 1.5. The key being that it's greater than 1. So I'm going to go ahead and give this a general shape. It might not go through all the exact points it's supposed to, and that's okay. If you were taking a test and you wanted your graph to be really nice, you could find a point on the, that was definitely going to show up in the other quadrant, but you know it's going to look like that. So we're just going to draw it because, again, our purpose are limits. And today's purpose is to make sure that you remember how to graph all different kinds of functions. So there's a graph of a rational function. And hopefully all of this is coming right back to you. Okay, sine is strictly memorization. You must have the graph of sine memorized. Sine starts at 0. Its period ends at 0, which is 2 pi. It has a length of 2 pi. And in the middle at 0. This is how I always graph it. Starts at 0, ends at 0, the middle at 0. In the middle of the middle, pi halves, it's at 1. In the middle of the other middle, it's down here at -1. I know that's not really fancy terminology, but it's just the easiest way to think about it. When the period changes, we can still think about it as the beginning, the middle, and the end. Personally, I wouldn't draw it until you finish all your dots. Chances are much better for making a really smooth, continuous curve when all the dots are drawn in. Nothing to remember here, just everything to memorize. Gotta know sine. So I wanted to do another rational function. And on this one, you'll see that the power in the numerator is different than the power in the denominator. And up here, I had specifically said that you need to be comparing A and B for when they have the same power. So if you tried to make them the same, you'd have to add in here a 0x squared. So now your horizontal asymptote, A over B, would be 1 over 0, which, as you know, you can't divide by 0. So this is your little alert that it's going to have an oblique asymptote. Again, vertical asymptote is what makes the denominator equal to 0. So I can see that 5, it will never be 5. 5 would give you a 0 in the denominator. So right away, I can make my vertical asymptote at, that's not 5. I can make my vertical asymptote at 5, and my oblique asymptote is going to be found using long division. So I've got my x minus 5. It's always easier when you put the placeholder in. So x times x is x squared. X times -5 is -5x. Don't forget to change the sign. Now I have 5x plus 25. I add 5. I get 5x minus 25. I change. What did I do wrong? Oh, that's it. I was going to say there's a mistake somewhere. So right here, that should be a negative because I knew that they were going to cancel. So this is supposed to be a minus. This is a minus. And now when I change the sign, minus and plus, I get 0. So there's no remainder. There could have been a remainder. It wouldn't have actually mattered, but I just knew there was a remainder of 0 and wanted to make sure that it was accurate. So what you need to know is this part up here, add a y is equal to it, and that is your oblique asymptote. So I'm going to start at 5, and then I'm going to go up 1 and over 1, up 1, over 1, up 1, over 1. So it looks something like this. And then, of course, I told you the next thing to do would be to plot a point. So again, most people pick 0 because it's easy. 0 right in here would give you negative 25 over negative 5, which would give you positive 5. And then, wait 1 minute. So that actually lands on the asymptote, which is not impossible, but should be an alert that something's wrong. If you actually kept plotting points, you would find all of the points land on the asymptote. So this is a little bit of a warning that maybe you need to think about this problem again. And here is the thing that you need to know. Always factor and simplify first. You're going to forget, and that's okay. I want to show you by doing it this way that you can forget, and that's okay. But this problem can be rewritten as y is equal to x minus 5 times x plus 5 over x minus 5. This problem is literally just the line y is equal to x minus x plus 5. It has no, just going to make it a little thicker so you can see it. It has no asymptote at all. It is the asymptote. It is the line. So what does that mean for the vertical asymptote? It doesn't have one. It just is this line. But what it does have is a little hole right there. Because if you were to type the original problem into your calculator, it still won't allow you to plug in an x is equal to 5. That's not allowed. So there's a little bit of a gap there. Okay. You probably actually can't even see it on your calculator. Oh, and look, it's so small, didn't want to draw it. So I'm going to draw a big hole. And that's what that one would look like, which is going to be important for limits. So be careful, factor and simplify when you need to. Okay, next graph, absolute value graph. If you'd forgot, these make a V. So y is equal to the absolute value of x plus 2 minus 1. And the number that's with the x does the opposite of what you think. So it's minus 2. And then this number does the same. So it's minus 1. And that'll give you the vertex of your V. There's no a here. Meaning there's no slope. There's nothing that's stretching it or shrinking it. So it's just going to go up by 1 each time. And you might remember that I said I personally always draw the dots first because I'm really bad at drawing lines, but I'm pretty decent at connecting the dots. Absolute value graph. Hopefully you remember that one. Another rational function. So there are 3 because there's 3 different situations. Again, you need to compare for the horizontal asymptote. You're always trying to compare A over B, but you can only do that if the powers of x are the same. So we can't just get rid of the x squared, but we can add an x squared on the top, but it's 0x squared because there's none of them. So now A is 0 and B is 1. So 0 divided by 1 is 0. So be careful not to confuse that with this one, which is 1 over 0, which you can't do, and that tells you that there's an oblique. You can do 0 over 1. So the horizontal asymptote is y is equal to 0. Some kids choose to just memorize that whenever the power of the numerator is less than the power of the denominator, it's always going to be y is equal to 0. But other students really like to have always comparing A and B, which you can always do it that way. To find the vertical asymptotes, remember that we're going to find the vertical asymptotes by setting the denominator equal to 0. So that would be x squared minus 4x minus 5 is equal to 0. Don't forget that whenever you see an x squared in an equation, set it equal to 0 and factor. So I'm going to factor this. We're in calculus now. I'm not going to spend any time talking about how to factor. and we get x is equal to 5 or x is equal to -1. If you were solving, you'd be saying either one of those answers is good. In this case, you're doing asymptotes, so both of them are asymptotes. So there's going to be an asymptote at 5, and there's going to be an asymptote at -1. You may remember from this H pattern that it usually means it's something like this. That could be one of the possibilities. Or it could be this. Remember that it can cross the asymptote. It's not that it's impossible to cross an asymptote. It's impossible to cross a vertical asymptote, but not a horizontal or oblique asymptote. So it's going to be one of those. Well, unfortunately, if you were plotting points, you would start to get very, very stuck because, and this is definitely going to happen to you, warning, factor and simplify. So maybe some of you were laughing because you had already thought of that. Awesome. I'm so happy for you. But if you hadn't and you got suckered in again, then you are definitely need to have this on your list of things to watch out for. This can be simplified. This is literally just the equation y is equal to 1 over x plus 1. It only has a vertical asymptote at -1. There'll be a hole at the other spot, but not a vertical asymptote. So we're going to go ahead and get rid of that asymptote. There is still a horizontal asymptote at y is equal to 0, because if you think of this as x to the 0 up here, or I should say 0, x to the 1, it's still 0 over 1, so it still works. Just going to erase that. And like usual, I just pick a point and plot it. 0, 1, and I have myself a graph. Now, technically, when you get here, there's a hole because you still can't let 5 be something that you enter in. Okay? And that's that graph. So those, we've done a couple rational functions now. They're probably the most challenging for kids at the beginning of the year. But we do a lot of rational functions in calculus, so you'll get good at it. All right, on this next one, I'm actually going to make 2 graphs. The first one is just the standard graph for cosine. I just want to make sure that you know it. So cosine starts at 1, ends at 1. It also has a period of 2 pi. And at the middle, it's -1. So cosine of pi is -1. And in the middle at pi halves, it's 0. And at 3 pi halves, it's 0. Again, I like to draw it all the way across, but I can't stress enough how important it is that you have this one memorized. I'm going to make it dotted because it is not the graph that I want for this problem, but I want you to have it in your notes that this is the graph, the parent graph of cosine. So how does the -3 affect it? So you might remember that the -3 affects it by its amplitude. So I just take every value and multiply it by -3. So 1 would go to -3. 0 would stay at 0. -1 times -3 would be +3. 0 times -3 is 0. And 1 times -3 is -3. But it still follows the same pattern. Starts at -3, ends at -3, in the middle at +3, and it's 0 in the middle. So I'm just going to go ahead and finish plotting my points because I do better drawing it when I can see the points ahead of time. Still not awesome, but better. There you go. That's -3 cosine theta. All right, this next one is a little bit of a trick. I've been focusing so much on rational functions. People look at it and think that it's a rational function because they see a fraction. But I need you to get used to the fact that you might see this and you need to be able to rewrite it. This is just a parabola. Okay? If you ever have 1/2 x, that is the same as x over 2. Some of you are like, duh, but certainly this is a concept that people miss. So thought I'd put an example of that in there. But otherwise, it's just a parabola. It hasn't moved left, right, up, down, but it does have a stretch factor of -1/3. So I'm not going to move it left or right. I'm just going to start at 0, 0. But instead of 1, 1, I'm going to multiply that 1 by -1/3. So I'm just going to go to -1/3. And instead of 2, 4, I'm going to do 4 times the -1/3. So it's -4/3, which is only 1 1/3. It's right there. So it's much wider and it's down. Remember, 1/3 would make it wider than a normal parabola. All right, last graphing example. So I know, another rational function. Sometimes the simplest ones can be the hardest. So horizontal asymptote is a over b. Now you have to put the x in there so you can be comparing x's both times. So it's 0 over 1, which is just 0. So the horizontal asymptote is y is equal to 0. The vertical asymptote is letting the denominator, x, be equal to 0. So this is the vertical asymptote. And then you just pick a point. So this example is in here because I said I always just pick 0, but you can't pick 0. But you can pick any other number. I'm going to pick 1. Or I could have picked 2. I can pick anything. There's lots of points to pick. So when you can't pick the y-intercept, and that goes for any kind of equation, if you can't pick the y-intercept, pick something else. And then this one, like I said, in calculus, I'm going to look for a lot of great graphs that have good general shapes, but not necessarily all exact points, because our main goal is to study limits. So that's the end of our review for graphing. You can go to the next video and actually learn what it means to be a limit using all these graphs. Thanks, and have a great day.